In this video, we're going to continue our discussion of ionization energy. Ionization energy is defined as the amount of energy required to remove the most loosely bound electron from a gaseous atom in its ground state. And we've seen that there are some periodic trends related to ionization energy. For example, ionization energies tend to increase as we move from left to right across a period. They tend to decrease as we move down a group on the periodic table, and they tend to decrease when we start a new period on the periodic table. Now, there are some deviations and exceptions to these periodic trends, and that's what we want to discuss in this video lecture. So, for example, here's a periodic table which has the ionization energies listed, and let's look at the second period. As we move from left to right, we see that the ionization energies tend to increase, and that's what we would expect. Same thing with period 3. They tend to increase from left to right. However, there are a couple of exceptions. If we examine beryllium and boron, there's actually a decrease in the ionization energy between beryllium and boron. And we also see this trend right below it in period 3, going from magnesium to aluminum. Now we see one other exception or deviation to this trend. When we go from nitrogen to oxygen, there is a decrease in the ionization energy between these two atoms, as well as those right below it, as we go from from phosphorus to sulfur. We also see it a little bit from arsenic to selenium. So the ionization energy does not steadily increase from left to right. It generally does, but there are a couple of exceptions. Now, often you'll see this this table shown graphically. So let me just show you that as well. And you may want to pause the video and carefully look at this. Let me go through it, but pause the video and take a look at it. Here we have lithium. So this is the start of the second period, and we go up to neon. This is the end. So as we go up here, we can see that as we go from lithium to neon across the second period, the ionization energies tend to increase, meaning it gets harder to pull off an electron. And then here, period 3 starts with sodium to argon. Again, the ionization energy tends to increase from left to right there. But here we see that exception between beryllium and boron. There's a slight dip, and also between nitrogen and oxygen. And we see that here from magnesium to aluminum, and between phosphorus and sulfur. So why do we get a decrease in the ionization energy between beryllium and boron and magnesium and aluminum? And why do we see a decrease in the ionization energy as we go from nitrogen to oxygen and phosphorus to sulfur? So let's try to explain these two deviations from our periodic trend. And let's look at beryllium and boron and then nitrogen and oxygen to illustrate these two things. So the first thing I want to do is draw out the arrow notation for beryllium and boron's electron configuration, because that's going to give us a lot of information. Now here I have the outermost highest energy electron colored in red, and that's the energy that the electron we're trying to remove. Now our deviation in our trend tells us that it is actually easier to remove this electron from boron than it is this electron from beryllium. So it's harder to remove the electron from beryllium compared to the outermost electron from boron. So why is that? Well, it turns out that here with boron, we are starting a new subshell. We're putting an electron in a p subshell. An electron in a p subshell is a higher energy electron than an electron in an s subshell. That's because of the shapes of these orbitals. Remember, s orbitals are spherical, and so therefore the electron is going to be closer to the nucleus. It's going to have a higher probability of being closer to the nucleus than a electron in a p orbital. And so therefore, when you have electrons in s orbitals, because of the shape of the orbital, there's a higher probability that this electron here in beryllium is going to be closer to the nucleus, and a lower probability that this electron in boron would be closer to the nucleus. So therefore, since this electron is closer to the nucleus, it's going to be harder to remove than the electron in boron. So to sum that up, with boron, we start a new subshell, not a new shell, but a new subshell. The p electron in boron is further from the nucleus and higher energy, and therefore it takes less energy to pull this off than compared to the electron in beryllium. And we could say that same thing from magnesium to aluminum. Now, what about our other trend here, the nitrogen and oxygen? Here with nitrogen, if we look at the electron configuration, we see that we would try to remove this electron from nitrogen, and oxygen, we would be trying to remove this electron here in red. So we're saying that it's actually easier to remove the electron from oxygen than this electron from nitrogen. So why is that? Well, if we look at the electron configuration, we see that the electron in oxygen, the outermost electron is oxygen, in oxygen is paired up with another electron, whereas all of the electrons in nitrogen, each one is in their own orbital. Now, when you put two electrons close together like this, there's going to be some electron repulsion because both of these are negatively charged. So because of that, the electron that's added to oxygen, this outermost electron, feels an additional repulsive force that's not felt by this electron in nitrogen. So this electron, because there's some electron-electron repulsion, it's going to be easier to pull off that electron in oxygen, resulting in a lower ionization energy. And again, we'll see this similar trend if you compare the electron configurations between phosphorus and sulfur. So these are two electron exceptions or deviations from our general trend for ionization energy. Be sure you can explain these and understand why these deviations take place.